Hey everyone. In this video, we are going to be talking about two related concepts. And these two concepts are efficiency and power. These are two new concepts to the unit, but they interconnect very closely with all the other things we've been doing, which are like work and energy and force. We now have two additional concepts, efficiency and power. And we're going to explore them in this video because they're pretty closely related. Before we get into precisely what efficiency and what power are, there's one thing we need to look at in a little detail, and these are things called energy transformation equations. And what these are is essentially these equations that convert energy from one form to another. We learned last time about the law of conservation of energy, which tells you that the energy never changes. The amount of energy never changes, but it changes type from one type to another. And so these equations, they're not very much like equations, they're kind of just like explanations using symbols, tell you how this works. So I'm going to use an example, and the example I'm going to use is cooking a pizza slice in a microwave. And I'm going to write out the equation, and then I'm going to explain what on earth I mean. So this is the equation for this pizza cooking in a microwave. And it might look a little confusing initially, but it will make more sense once I've done it. Ignore that. Okay. So this is the equation for pizza cooking in a microwave. So the first thing you'll notice is there's kind of three steps here. There's this portion, there's an arrow to this portion, there's an arrow to this portion. Most energy equations, but not all, have three. You can have more steps, you can have less steps, depending on the thing that you're modeling. But in this case, this is kind of the before, the during, and the after of the cooking of the pizza. Not exactly. It's more accurately, this is when it starts cooking. So it started the cooking here. Then it's going to begin running here. And then the pizza is going to cook here. Kind of a before, during, after, not exactly. And so these phases each have different energies. And we don't care about the values at all. This is just the types of energy at each phase. So at the beginning, we start with EE, which is electrical energy. And we start with electrical energy, and because we're, of course, powering this microwave from an outlet, probably in our wall. That electrical energy is going to get converted when it starts running, and it's converted to three types of energy. ERAD, which is radiation energy, and that's, of course, the microwaves. After all, it's a microwave. It cooks the food using microwaves. That's the radiation energy. Also EK, which is kinetic energy, because, of course, the disk is spinning around in the microwave to cook the food evenly. And then there's E-sound, which is the sound that I'm sure you all know a microwave produces. And then finally, when it's cooking, you're going to get this thermal energy, which is clearly the heat, which is cooking the pizza. So this is how an energy transformation equation works. And it's basically that simple, but you might need these a little bit to understand how systems work. And it's always a good idea to make them if you're ever confused about what to do in a question. Okay. Off of energy transformation equations, we can talk about the actual concepts of this section. And we're going to start with the first one, which is efficiency. Let's learn what efficiency is. We all kind of know intuitively what efficiency is. It's how efficient is something. Are you an efficient person or an inefficient person? Is your appliances, are they efficient or inefficient? Things like that. But efficiency has a very precise definition, and it's basically the amount of useful energy that's produced in an energy transformation as a ratio or a percentage of the total amount of energy. I'll explain what I mean. First of all, useful energy. What do I mean by that? Well, when I say useful energy, I mean basically the energies that we care about in a specific system. Because usually there's byproducts, other types of energy that do not matter to us as much as some specific thing. For example, in our microwave example here, this kinetic energy, this sound energy especially, because it's annoying, we don't care about those. Those are just kind of unnecessary byproducts. If we could get rid of them, we would. But the thermal energy is the thing that we actually need. It needs to cook the pizza. And so the thermal energy here is the useful energy here. So efficiency is the amount of useful energy that's produced in one of these transformation things. And it's very simply defined. We usually use EFF to represent efficiency, and it's equal to the output energy divided by the input energy. And you want to express this as a percentage. Like this will give a decimal. You might get like 0.38, but that's 38%. So some people will say percent efficiency equals this times 100% to make it clear that you need to convert this to a percentage. But I'm just going to leave it the other way for now. So efficiency is E out equals E in. That means that if you're dealing with a thing where you put in 1,000 joules of energy and the only useful energy you got out is 100 joules of energy, well then you would do EFF for this system equals 100 joules divided by 1,000 joules, and of course you cross out the zeros, you get 10 joules. You get 1/10, not joules, it's efficiency. And so you get 0.10, which is just 10%. And you realize that your thing is 10% efficient, which is completely terrible. Hopefully nothing you have is 10% efficient in your house. But this is the concept of efficiency. It's also worth mentioning that I'm dealing with E out over E in here, but that's exactly the same as W out over W in. That's work. But because work is just the change in energy, delta E out over delta E in, change in energy, is the same as saying work out over work in. And these are very important. Efficiency is a very useful concept in a lot of things, and in questions where you might be given an input energy and an output energy, or an input work or an output work, or as we're going to see in a second, an input power and an output power, you can use this efficiency in a lot of ways. Knowing that ratio is often helpful. So that's efficiency, and we're going to counter efficiency with a discussion about this other important concept, that of power. Power is another thing, like most things in physics, that we kind of have a concept of in the real world. Like we know something is very powerful, and physics has a very, very much more strict definition. Power is the rate at which work is done. Okay? Rate at which work is done. Another way to think about this is that it's the rate that energy transforms from one form to another. When we say rate, we're implying that we're talking about something relative to time. Just like acceleration is the rate at which velocity changes, and velocity is the rate at which position changes, these are all over time. Remember, velocity is distance over time. Acceleration is delta v over delta t, always over time. So power is also a thing over time. And what is that thing? It's work, because it's the rate at which work is done. So power is defined using the letter P as the net work over the change in time that work is done over. And because net work is the same as change in energy, you could also say that power equals delta E over delta T. This is the equation for power. Again, something you'd probably want to put on an organizer or somewhere you can keep it so that you know what you're doing. Power is measured in a unit of that you can say two ways. You could say joules per second, because this is just technically correct. You can see quite clearly that work is done in joules, or the change in energy is done in joules, and then the time would be done in seconds. And so these are just transparently, you're taking joules and dividing it by seconds. The unit is joules divided by seconds. But joules per second has another name, and it's the watt. And this watt, named after a guy named James Watt, is the unit, and it's literally 1 joule per second equals 1 watt, and we indicate it with W. So W is literally just a shorter unit for joule per second. They mean exactly the same thing. And this concept of power is kind of important. In fact, we use it a lot. You might have seen you have light bulbs in your house which are rated at a specific number of watts. It's telling you it's a 60 watt bulb. And what is a 60 watt bulb? Well, we now kind of know. If you have a 60 watt light bulb, that is 60 joules per second, because joules per second and watts are the same. That means, quite simply, that every second that bulb is dispersing about 60 joules of energy. The delta E, the energy is being transformed at a rate of 60 joules per second. Or put another way, 60 joules of work is getting done every second by that bulb. And in the bulb's case, that, depending on the type of bulb, is converting electric energy to thermal energy, more or less. You could say that, and you could write a transformation. There's some other factors in here, but that's the gist of it. And this transformation here is happening at a rate of 60 joules per second. And that's the concept of power. So this is a pretty short video because there was really only two things to get here. Efficiency, which is the ratio of energy out over energy in. It's how much energy is in and how much useful energy is out. Because remember, in an isolated system, the total energy will not change. But it's the useful energy that we care about here. How much energy is actually being used in this process. You know, if you're cooking something, you care about thermal energy, but probably not about sound or light energy. Also, we talked about power, which is the rate at which work is done, or the rate at which an energy transformation occurred. And it's measured in watts, and it's equal to W net over delta T, or delta E over delta T, depending on whichever way you want to state it. And these are these two kind of important and interconnected concepts, efficiency and power, and they connect back to all the other concepts in this unit. Because after efficiency and power, we now have energy, we now have work, and we've connected them all together into one thing. This is, in a sense, the last kind of two concepts of this kind of section of the unit, where we're talking about work and energy. Because we now know work, energy, efficiency, power, and lots of equations for how they're related. And now it's a matter of doing questions that interconnect them. And that's basically how this works. Hopefully this video was helpful. You understand a little more about efficiency and power. And I will see you guys all next time.